Right, welcome back, welcome back. Um, Sorry for the delay. Um, okay. Last time when we spoke, we were speaking about titration, right? Titration. So we spoke about titration, and we said if there is no neutralization between substances or between your chemicals, then there won't be any titration. So now I want us we go, because the last time we parted ways, we were about to speak about what do we call pH, right? Now let's get to it. What is pH? pH of a solution is the number that indicates the degree of its acidity or basicity, right, of the solution. It determines the level of acid of that acid, and it also determines the level of that base, right? So now we know that from pH we have what we call the pH scale, right? So now with this we can determine that pH is equal to negative log of what? The concentration of the hydronium ion, like that. Then also we can say that pH is equal to log 1 and the log of the concentration of the hydronium ion. This simply just means one and the same. So it doesn't really matter. So yeah, how did we come up with this equation and not this one here? So what basically happened is that with the laws of log, if you have log of A over log of B, then this will give you log AB. So practically here we have 1, so it's just log of B. It doesn't make any difference even if we put 1. So now that's why you see this here. So this is not compulsory, this one. You can just take this, it's already simplified. So now we're not gonna talk about that much, right? So basically that is what I wanted us we talk about. So now note that acidic solutions have a pH that is less than 7, right? Now why is that? Because the concentration of the hydronium ion, sorry, I put it in the wrong way. The concentration of the hydronium ion, right, it's going to be greater than 1 times 10 to the negative 7, right? Now that is the main reason. So with the neutral solution, right, what do we have there? We say that this is supposed to be pH, right? This is supposed to be pH right here. The pH, like that. Now the pH of the solution is equal to 7. Why is this, right? Because the concentration of the hydronium ion, right, or the solution, is equal to 1 times 10 to the exponent negative 7. Now we have the base. Now with the base solution, we know that the pH is greater than 7, right? Now the hydronium, the concentration of the hydronium, right, in this case, or the solution, is going to be less than 1 times 10 to the negative 7, right? Okay, maybe you may not understand why we said this is greater than 1 times 10 to the negative 7. Basically because remember, with the increasing values in the negative side or after the comma, right, it empowers this one here, right? Now with the decreasing value, it gets nearer and nearer to the pH of 7. So the reason why we say this hydronium or this solution is going to be less than 1 times 10 to the negative 7 basically is just that, right? So now the pOH scale is similar to the pH scale, and it refers to the negative logarithm of the hydronium ion, hydroxide ion concentration of the solution. So basically in this form we'll be speaking of the base, because this hydronium here represents an acid, right? So now we are talking in terms of the base. Then we have what? Log of what? Of OH, the hydroxide ion. Now that is good. From the product of water, remember that the last time when we spoke about this Kw, we said is equal to the OH negative, the concentration of the hydronium, multiplied by the concentration, the concentration of the hydroxide multiplied by the concentration of the hydronium, right? Remember this was 1 times 10 to the negative 7, right? Multiplied by what? 1 times 10 to the negative 7. All of this, it gave us this solution, 1 times 10 to the negative 14, like that. So now here we were left with 1 times 10 to the negative 14, right? Now that's basically what we need to look at. So now we have another solution that we can use for now. So now let's try to solve this. We have your log. Remember here we said the pOH and the whatnot and whatnot, right? So now what we can say is that the log of the concentration of the OH, the hydroxide, plus the log of the hydronium ion, right, is going to be equal to that 1 times 10 minus 14, right? Let me try to move this. Where is the other one? I want to move it to this side like this. This is 14, right? So now we have this net here, so we can conclude and say the log of the hydroxide ion plus the log of the hydronium ion, the concentration, right, is equals to 14, right? So now we can solve this thing. We can conclude to say, remember, this is the pOH, this is the pH. So we can say the pH, right, plus the pH OH, right, is equal to 14, like that. So now what you're going to do is that you're going to solve it in terms of the what do we call it, the scientific notation, then get the value in this form, then find the acidity or the like alkalinity of that substance in terms of this formula here, right? So yeah, we will deal with this step by step, right, so that you can see it. We are given an example here. They're saying to you, calculate the pH of a molecule of sulfuric acid, H2SO4, right? Sulfuric acid, H2SO4, which has the concentration of 0.025, right? So now they're saying calculate the pH of that. So now remember, 1 mole, if we try to simplify this, we are saying what? 1 mole of sulfuric acid ionizes completely to form 2 moles of the hydronium, right? Basically, we're still going to use the formula H2SO4 plus H2O is going to give us H3O plus, then a plus what? The H SO4 negative, something like this. So now what are they saying? If we want to balance this, right, here we're going to have to add a 2. Now this is 4, right? This side is 4, this side is 4, 3, right? So we're going to have to add 2 here, right? So that we can have 6. Let's see, we added 2, we added 2. How much do we have here? We have 4. This is 8, and this is what? This is, okay, 6 plus 2 is 8. Then here 4 plus 2 is going to be that, right? So what's gonna happen if we put 4 here? It's gonna change the whole thing. I think I did not write the correct equation here, right? I did not write the correct equation here. Let me remember what is going to be here first, before I conclude, right? Let me check it. If we have the sulfuric acid and we want to have the hydronium oxide, then that we need to do what? What are we going to have? If we add water, what are we going to have there? You have your I'm trying to think about it. Yes, we have to add water. So yeah, basically this is where I was wrong. We're not going to have another hydrogen this side. It's just gonna be your sulfate, right? SO4 minus. So yeah, basically we're going to have a 2 here, right? Which is going to be your 6, okay? So here we can have a 2. Are we going to have a 2? let me see, 2 hydrogen 2 is 4, then H3, let's see, now we can still add another 2 here, right? Then add another 2 here. Let's see, we're going to have 4, then it's 6, then we have 2 here, then it's 6 for this one. Here we're going to have 6 straight up. So here we're going to have what? 2 plus 4 is 6. Yeah. So this is how basically you can write the equation, right? So now note that on this sulfuric acid it's 1 mole, right? On water it's 2, then on this hydronium is 2. So now in this solution we said that 1 mole of H2SO4, the sulfuric acid, ionizes completely to form 2 moles of the hydronium, right? Therefore, the 0.025 mole of sulfuric acid will yield 0. If we multiply, here we have what? Your 1 multiplied by your 0.025, right? Then for this hydronium, we're going to have 2 into 0.025. Remember, this is 1 mole and this is 2 mole. So for this one, we're going to have the concentration of 0.05 according to Kc, right? Equilibrium constant. So now what we can do is that we can simply say, remember, to find the pH, we're going to say the pH is equal to what? Negative log of the hydronium, right? Plus, then from there substitute, we have negative log of what? Of 0.05, right? And this will give us what? Let's see, 1.3 knot. That is basically the concentration. We have to put it in the hydronium form, right? So let's check this other example. Let's check this other example. So let's deal with this other example here. Let's say you have this solution that they are going to give us. Calculate the pH of the 0.01 mole per dm of sodium hydroxide. Basically, the solution of sodium hydroxide is going to be NaOH negative, right? Then when they say solution, it means either they're going to add it with water or something, right? Now, what are we going to have? We're going to have the hydronium like that plus the sodium. This will come here, right? Yeah, we're just gonna have this sodium, I think it's supposed to be sodium oxide, right? So now we're gonna have to try to balance this. This side we have 2 hydrogens, here we have 3, so basically we just have to add a 2 here. Then we want to have 6, right? And for this one, if we add a 2 here, we're going to have what? 4, right? Then let's add a 2 here. Now let's see how much. This is 6, right? So this is going to give us 4. Then if we add a 2 here, how much do we have here? We have 2 plus 2, which is 4. Here we have 2 plus 2, which is 4, right? Then for this one, it's going to be 2 plus 4, which is 6. Then this side already we have 6, then the sodium is 2, then it's balanced, right? Now, looking at it like that, since it is balanced, this means that you're going to have what? 2 moles, 2 moles, 2 moles, 2 moles, right? So now, okay, good. Let's come to the solution. Calculate the pH of the following solution. Now, listen, this is in terms of if we were to add water. So now, let's say calculate the pH of the sodium hydroxide solution. So now, in this form, it's going to take the sodium hydroxide, which is a solid, so they're going to crack it. When they crack it, it's gonna give us your sodium ion and your hydroxide. So now you have this. Having this, it's just 1 1 1. So here you have 1, here you have 1, here you have 1, right? If you were to use this solution here, you're going to have 2 2 2 2, right? So basically it was just, this side was going to be equal to this side, right? So now with this one, because this is a base, so we want to form the OH group, which is this group, right? So we have to crack it first. So now the mole there is 0.01. Then they say calculate the pH. So to calculate the pH, remember that the 1 mole of sodium hydroxide dissociates completely to form 1 mole of the OH negative, the hydroxide. Therefore, the 0.01 mole, right, of NaOH will yield what? 0.01 mole. It's mole per decimeter, right? Decimeter. Even here it's per decimeter, right? Of what? Of the OH, right? The hydroxide, like this. So now this is what we need to look at it. Then just remember something quickly, that if you have the H plus, right, the H plus will represent the hydronium, and you multiply it by the OH plus, the OH minus, sorry, then you're going to have 1 times 10 to the negative 14. Now let's try to solve it in this instance. Remember, here we have a H plus. We want to move this OH to the other side, so we'll have to divide. Therefore, the H plus, or the hydronium, is going to be what? 1 times 10 to the negative 14 divided by the concentration of the hydroxide. Then you have 1 times 10 to the negative 14 divided by what? It's divided by 0.01, right? Now that answer that we get there is going to be what? 1 times 10 to the negative 12, right? So now we want to find the pH of this. The pOH, or rather the pH, is going to be negative log the concentration of the H plus, right? Now what do we have there? If we say that is the pH, then this is going to be what? Negative log of what? 1 times 10 to the negative 12, right? How much do we get there? We get 12, right, as our pH. So the pH of that is 12. Now find the negative log OH and subtract it, right, from 14, right? So you're going to say negative log of that. So basically this is the solution, right? So you can take another route and try to solve it. Remember that the log of the hydronium ion, right, plus the log of the OH ion is equal to 14. So basically, to find the log of this, you're going to take this one to the other side, which is going to be what? Log of OH minus is going to be what? 14 minus 2, and going to get you 12, right? So that's just how we can do it as extra knowledge, but I don't prefer this. So yeah, that is basically that. So now I want us we look at this. Let me check. Yeah, we're left with nothing. Let's just conclude this. The acid and base dissociation constants, right? We have the Ka, the and the Kb, right? Now we can represent the net ionic equation for neutralization between acids and bases. So what I need you to understand, why do they put this hydrogen ion here? It's because of this yield here, right? Now this one here has lost a hydrogen, right? So this one here is our acid, right? It's not necessarily our acid, but it has a proton, so we consider it to be 1. So this one here is going to be our base, right? So we're going to, instead of putting an A plus, we put our H plus, right? Then if you don't want to put this, you can just put the hydronium ion like this to show that you're calculating for that. So now the dissociation constants, it's Ka and Kb, right? So you have your, let's say you have this solution, H plus your OH, right? We know that this is going to react to form H2O, right? So now these constants react between what? We can represent the net ionic equation for neutralization between strong acids and strong bases. Hydrogen ion, which is a strong acid, and a hydroxyl, which is your strong base, right? So now most acids are weak and do not ionize completely in water. The organic acid, the ethanoic acid, ionizes as follows, right? Let's try to check your ethanoic acid. With ethanoic acid, it's going to be CH3 COOH, right? So now plus water H2O, we know that this is going to be CH3 COO negative, right? Then plus your hydronium here ion like this, right? So now this is a forward and a backward reaction, okay? Even this one here, there has to be a forward and a reverse reaction, forward and the reverse reaction. This is according to equilibrium constant, right? So now the equilibrium constant of this equation here, this one, is going to be what? Your products divided by your reactants. So it's going to be your CH3 COO negative, then the concentration of the hydronium divided by your CH3 COOH, then your water, something like this. So now that is the Kc. So now, but water, the concentration of water is practically constant for dilute solutions. Then the new constant Ka, which represents the constant of acid, is going to be equal to what? CH3 COO negative and what? H3O plus divided by your CH3COOH, something like this. So now that is your acid dissociation constant. This is the acid dissociation constant. So now, yeah, that's basically that. So the similar thing is going to apply with bases, right? So you look at the point where you have your water, then you remove the water from the Kc equation, then you change it into your Kb. You're going to follow the same procedure. You see here we just removed the water, then we're left with the entire thing, but we put the acid dissociation. So if this was a base form, so we were going to remove this water and write Kb, right? So yeah, that's basically that. That is basically that. We can do it for the base, so I can be sure that we did it together. So here we have your NH3 plus water. We know that this will give us the forward and the reverse reaction of what? NH4 plus, then plus your hydronium, right? So now we have water. This is the Kc is going to be the product of the NH4, right? The NH4 plus, right? Then here we're going to have your OH, right? Then divided by your NH3, the concentration of the NH3, multiplied by the concentration of water. So now for Kb, we remove water, then we just write what? The concentration of NH4 multiplied by the concentration of hydroxide divided by the concentration of the ammonia, something like this. So now we are done with the chapter. So hit a like the page and tell me, give me feedback basically. Yeah.